Hi, I'm Jeff Bier from the Embedded Vision Alliance. Today I'm very excited to be talking with Scott Krig. Hello, Scott.
Hi, Jeff.
Scott is the author of a brand new book, Computer Vision Metrics. Really interesting, excellent book, and I'm really excited to have the opportunity to talk with you today, Scott, about the book. Why don't we start with a little bit of background? Can you tell us a little bit about how you got started in computer vision?
Sure. Back in the early 1980s, when there were things like card readers and rack-mounted computers and CRT displays, I worked at Boeing in the advanced computer-aided design research area. And we added a frame buffer into our VAX 11780. And it was a Barco frame buffer, and it was NTSC resolution, 640 by 480, and that enabled us to do renderings. We were the cat's meow in Boeing. We could do renderings, and I was instantly attracted to the pixels and the lines in the frame buffer versus the graphics. And so that was my first exposure to graphics.
Mm-hmm. And how did that take you to a career in computer vision?
Well, I was actually kind of scared off with the computer graphics math, the biquintic patches, bicubic patches, all of the different aspects of graphics rendering. The NURBS came out of our lab. But it turned out that even though I went towards imaging, the math was equally complex but more diverse, because there's a vast universe of mathematics that's used for imaging and computer vision. So once I had left Boeing, I actually went to work at Pacific Western Systems on Mercer Island, and we were building automatic wafer probers. And the automatic wafer prober could see. We put a camera over the wafer chuck so we could see the wafer, and we had to find patterns on the wafer and line things up. We used correlation. We could find 4 32 by 32 patterns in a quarter of a second each, and we had some sub-pixel accuracy there using correlation in fixed function hardware. So that was where I got started.
So the machine found where to place the probe
Exactly.
using computer vision. And what year was that?
That would have been probably 83 when I felt like I had mastered it pretty well.
So pretty early days for computer vision and an industrial application, which has been pretty typical of computer vision deployments over the
Yes.
past decades. Very cool. So, what prompted you to decide to write this book? There's certainly no shortage of computer vision books out there. Why did you think the world needed another computer vision book?
Okay, that's a very good question. And if we look at the history versus the current state of the art, there's kind of a sandwich in between. The early state of the art was a lot of signal processing, a lot of correlation. Some of the earlier techniques, military kind of introduced those, and they went into some industrial applications. And then if we go to the other end of the spectrum today, there is a lot of interest in local interest points and local features. So instead of using mugshots as you do in correlation to find the pattern, the image is divided into interest points with descriptors around those points to describe more information. But there's kind of a sandwich in between in the books. The earlier books, Rosenfeld, a lot of these earlier computer vision books, I don't want to name too many names because some of the books are still good. The earlier ones were more image processing and correlation, and the later ones were more OpenCV. And the most recent research is the interest points and descriptors, a lot of it anyway. So there was an opportunity to sort of look at the whole field and identify different families of computer vision methods.
Mm-hmm.
This book really is the only one I know of that tries to identify the families of computer vision methods.
That's great. Yeah, taxonomy can be really helpful. It's a rich field with lots of different techniques and understanding how they all fit together, how they relate to each other. Definitely helpful. So what sort of audience, what type of person did you have in mind as a reader when you were writing the book?
I would say there are two levels. One level is a high-level decision maker and thinker, such as people I worked with at Intel, vice presidents, fellows, really good engineers who need to understand the technology to make decisions for Intel, such as power envelopes, die area, software libraries, where it's going.
Mm-hmm.
So Intel looks at all kinds of technologies like that. At the other end of the spectrum, there's people who may understand parts of computer vision, but they haven't looked at all of it. They haven't looked at much more than they needed to do their job, the engineer level. And I suppose there's a third level, people that just want to understand what people are doing, what the practitioners are doing. So I'm trying to cover the bases, and if people need to go deeper, there's over 500 references in the bibliography to the research papers and how-to resources, OpenCV code, things like that. So I would say it's mainly for someone who wants to make engineering and scientific decisions, but not necessarily limited to a person who's an expert versus non-expert. I think people will find, depending on what they're looking for, they can find something in the book.
So how about an engineer in industry who isn't a computer vision specialist, maybe has done a little bit of reading, maybe a little bit of work in computer vision, and is now looking to do more with it, now that it's becoming practical to do more computer vision in more and more products. Would this book be useful to that sort of person?
I think definitely. Let me state what is in the book and what's not in the book. If we look at computer vision literature today, there is a mixture between what I would call computer vision and imaging and machine learning, because in real systems they're typically combined. What I've done is I've focused on the computer vision and imaging, the metrics. That's the title of the book, Computer Vision Metrics. What are these features? What do they look like? How are they designed? What is the mathematics behind them? What do they look like in memory? How is the processing set up? What are the little microalgorithms that are involved in creating these feature metrics? Then there's machine learning. After we have the metrics, how do we understand what we're looking at? I introduced machine learning, but this book focuses on a gap in the literature, which is what are all of the methods people are using? This is where the gap was. That's why I wrote the book.
You know, one of the things I like about the book is it certainly is about the techniques at the algorithm level, but not only about that. It also talks about implementation, and that's been, I think, a gap as well. There's so many books and so many articles and conference presentations on algorithms, but not so many on implementation, especially practical implementation. And I really like in, I think it's chapter 8, you have, I think, 3 examples, an automotive example and a couple of others, where you present sort of a complete pipeline from the sensor to the final output and explain what are the steps required to have a complete system, and talk about some of the implementation aspects like selection of processors and performance optimization.
Right. I would say chapter 8 is, it also kind of fills a gap, because as you mentioned, there are several examples of complete vision pipelines and how the different stages of the pipelines can be allocated to different kinds of processing. For example, there may be a DSP in the system, one or more CPUs with, maybe they have floating point instruction sets, maybe they don't, and GPUs, maybe the GPUs have enough execution units or CUDA cores, whatever you want to call them, to make them useful to compute with. Maybe there's enough memory to do fun things with memory. Maybe there's some fixed function hardware to use. Sure.
Yeah, so I think that's one of the aspects to me that makes the book quite relevant to practitioners who are not only interested in the algorithm techniques and kind of the theoretical aspect, but also how to actually build systems that are efficient, that are cost effective, which is usually what's required to build a product. What did you learn? You obviously did a lot of research in writing the book. It wasn't all just off the top of your head. What did you learn in writing the book that you found interesting or surprising?
I would say there's nothing new under the sun. A lot of the mathematics that are used in computer vision, people have been using since we've been using mathematics. It's just applied mathematics. Computer vision is basically a bunch of mathematical models and mathematical methods. In fact, in the preface of the book, I state that I view computer vision as a mathematical art form. So I guess the more I dug around to find out what is it people are doing, and what have they done, how is it different, how is it the same, I found out that there's not a lot new here in terms of the fundamentals, but there is a lot new with respect to the way the fundamentals are combined. So what I've done is I've tried to identify what are the fundamentals. We have global feature metrics, things people are familiar with, Fourier metrics, wavelets, maybe Zernike moments and polynomials. There's a whole bunch of things. That's chapter 3. Chapter 4 talks about some overall concepts for vision and some concepts behind the design of different ways to detect features.
Mm-hmm.
Are we trying to detect a global feature, a regional feature, or a very small local feature? And chapter 5 is a taxonomy of methods. What are people doing? What are these families? So I came up with some families of feature metrics. We got 4 families. I identified the basis spaces, global and regional metrics, local interest point metrics, and shape metrics. What's the shape of an object? And there's different families, and they oftentimes ignore each other because there's different applications for each one. But I tried to pull together the different methods people are using.
Mm-hmm. Now you said you view computer vision as a mathematical art form.
Yes.
That's an interesting term. Why do you think of it that way?
Well, basically I view math as a way to create tools to deal with different types of data. And sometimes the data needs to be projected into another space. For example, a discrete time domain space of pixels can be projected into a Fourier space. Everyone's familiar with that as far as engineers go. There are a lot of different spaces, and once the numbers have been projected or transformed to a different space using one tool, then other tools can be applied to the data to identify similarities and differences and do processing. So it's kind of like an art form. There's not a right or wrong way to do it. When you get in and look at what people are doing, you find out here's one way to solve a problem, and here's another way that solves the problem a little different, but the results are almost the same. So it's like art, or it's like cooking or something. There's often a lot of different ways to do things, and then the differentiation or the decision point can come when you decide if power is more important, if performance is more important, if memory footprint is more important. And really the key issues I've identified in chapter 5 are the robustness and invariance criteria. Do I need scale invariance, rotation invariance, blur invariance, on and on? And basically by adding algorithms together to achieve the invariance you need, you can solve your problem. And that's what this book does, is it gives you the Legos. So here's one method, a Lego tool. You can stack a SIFT descriptor with an LPQ, add blur invariance or something, whatever it is. That's the idea here, is I'm not proscribing, I'm describing what people are doing.
Yeah, one of the things I liked is I think in the appendix you have a list of the public domain or at least publicly available data sets that a lot of researchers have made available, since that's often how you decide which of the myriad algorithmic approaches is best is by testing the candidates against hopefully large realistic data set, and developing your own large realistic data set that's often a really expensive, time-consuming proposition. So if you can leverage existing data sets, that's great, and you've got a nice list in here of many of the existing public domain or publicly available data sets.
It's a starting point. I keep learning about more data sets, and it seems like every year when people publish papers, a few people need to invent new data sets. They'll use the old ones to test their algorithm, but then they need a new data set to test a new robustness or invariance criteria, and they just keep coming.
So in terms of industry applications of vision, we certainly see in the Embedded Vision Alliance that the improvements in processors and sensors are making it now practical to put sophisticated computer vision into all kinds of places where it couldn't go before, including really small and expensive consumer products, smart pens and mobile phones, including cars, where we now see production cars incorporating sophisticated vision-based safety features, not only high-end luxury models, but also $30,000 mainstream models as well. What do you think are one or two of the key challenges for product developers who now see, now I can afford the processing power, I can afford the sensors, or maybe the sensors and the processors are already there, like in a mobile phone, and they have an idea of some new capability they want to implement with vision. What do you see as some of the key challenges these people are facing?
I would say the key challenge they would face is, number one, do I understand the solution, what it needs to look like. And when I say understand the solution, I would say we can divide that roughly into two sides. One would be power, performance, maybe silicon area, capabilities of the system. But then the other side of the problem is the robustness and invariance criteria. Do I need scale invariance? How much? Do I need rotation invariance? How much? Do I need light intensity invariance? What I mean by invariance is the vision method will find the same patterns or objects with the acceptable repeatability under variations in those robustness criteria. In other words, as the scale changes, we can still find it. As rotation changes, we can still find it. So to summarize there, understanding what needs to be built, because that will determine the kinds of techniques that are available to you.
Yeah, certainly it seems to be the case, and I've seen a number of examples of this where very quickly someone is able to create an initial kind of proof of concept of some vision functionality kind of in a lab under benign conditions, right? Good lighting and, you know, cameras not vibrating and so on. But then when the system's taken into the field with non-ideal conditions, and it often fails very quickly. And the amount of work required to go from that initial prototype that works under benign conditions to one that's really robust under realistic conditions, that's often much larger than the effort that was required to create the initial prototype. And I think that's sometimes surprises people. Oh, well, we got it working in a week. How hard could it be, you know, to get it deployed?
Exactly, and you mentioned the ground truth data set survey that was in here. And I think that people become maybe overeager. They'll buy an OpenCV book, they'll download the source code, they'll implement an algorithm, and they'll be so thrilled that it works. Well, that's great, but what it really boils down to is the ground truth data that you're testing against. Do you have different lighting conditions, whatever your invariance criteria are, scale, rotation, I mentioned a few, and have you really tested against those? You know, have you really done that? And that's a big job. It really is a big job.
Well, Scott, this has been great. Thanks so much for coming in to talk with us. It's a really great book. I think a lot of people are going to get a lot out of it, including the audience that the Embedded Vision Alliance focuses on, which is product creators in industry who may not be career experts in computer vision, but who are excited about learning more about computer vision and how to practically implement it in real products. So thanks a lot for coming in.
Thank you, Jeff, for the opportunity.
On the Embedded Vision Alliance website, you can find more information on the book, including how to download a free electronic copy of the book. We're also going to have reviews of the book on the website, and I hope, Scott, you'll join us on the website to continue the dialogue with the Embedded Vision Alliance community about the book and the topics covered there.
I'm happy to help.
Thanks.